Today we're looking at Glencoe Accelerated Math, Lesson 5-9 on similar figures. Similarity in similar figures fits in really closely with our scale models and our scale drawings, because shapes that are similar are drawn to scale, or they represent a scale. Because if something is drawn to scale, then that means that the side lengths of an image are different, but the angle measures are the same. Two images that are similar to each other, like similar figures that we look at today, the angle measures are the same, but the side lengths are different. Okay? What happens is that if shapes are similar to each other, it doesn't mean that, we can say that the book is similar to the movie because they have parts that are the same and parts that are different. Everybody knows that you've read a book and then you watch the movie and it's kind of close, but it's not exactly the same.
Yeah.
Okay. So, what?
Especially with the Harry Potter movies.
Especially with the Harry Potter movies, yes. Once J.K. Rowling wasn't on set anymore, directors took a little bit more creative liberties.
Yeah.
Okay?
Stupid.
Not an appropriate way to say it.
I agree.
That's your personal opinion.
The
So, when we're working with scale and scale factor, when we're working with similar figures, these similar figures, they don't have to be real life. They can just be two triangles, or two rectangles, or two quadrilaterals, or two pentagons. And they don't have to be regular. That means that all of the angle measures don't have to be the same. In a regular pentagon, all interior angles are the same measure. Okay, that would be like a stop, not a stop sign, but there are road signs, and all of those interior angles are the same. But you can also draw it in a pentagon as any five-sided figure. Can you draw it with different angle measures? Yeah. Absolutely. Most of the time when we draw a sketch of that shape, it's not going to be regular. We know that shapes are similar because angle measures will be identified as being the same. So, if we have two figures, all right, and we're going to look at example 1, and example 1 has triangles. So I'm going to draw in triangles. Do those triangles look about the same? Different sizes, but they look about the same? Okay. Here's how we identify the angle measures as being the same. We draw in arcs. The same number of arcs, and I might not be exactly the same as the book, and that's okay. Okay? So, the number of arcs can be used, or you can use arcs with hatch marks through them. Whatever is the same has the same angle measure. So what this says is that this angle and this angle are the same angle measure. This angle and this angle have the same angle measure. This angle and this angle have the same angle measure. Because the arcs and the hatches within those angles are the same. Does that make sense to everybody? Yes? Okay, so this is how we determine similarity. If the interior angles, or if the angles are the same, doesn't matter what the side lengths are doing. Those figures are similar. We can find missing side lengths of similar figures by using proportions. So, if my little triangle, I want to make sure that I get the notation the same as in the book. We have triangle A, BC, which has side lengths of 4 centimeters and 6 centimeters. And then we have triangle DEF, which has side lengths of 12 centimeters and X centimeters. It says that since triangle ABC is similar to triangle DEF, that one wavy line between them means similar. Okay, everybody look in your book at that symbol. Underneath the triangles it says since triangle ABC, then it has a squiggly, then triangle DEF. That means that they are similar to each other. Okay? And it says the corresponding angles are congruent and the corresponding sides are proportional. If we have similar figures, the side lengths will be proportional. Always, every time. So we can set up a proportion to solve for x. So if I have, and there's different ways that you can set it up. They have, I like to use little over big equals little over big. So that would say that my little size is 4, my big is 12, equals little of 6 over big of x. Okay? We cross multiply to solve our proportion. That gives us 4 times x equaling 12 times 6. What's 12 times 6?
Oh.
72.
Like, who knows?
72. 4 times x simplifies to be?
4.
What do I do from here?
Divide by 4.
Divide by 4. Why am I dividing by 4?
Make sure that the x is by itself.
To get the x by itself. 72 divided by 4 is what?
18.
X equals 18. What units go with this? Centimeters. Okay? Check me in the book. Did they get the same thing?
Yes.
Yes. All right, good. Questions, comments, concerns? How is this similar to what we did with our scale factor? What is this similar to what we did on Friday in our previous lesson? Is it similar to what we did? Yes.
You're just using proportions to figure out the scale factor.
Right, so in both we're using proportions to find missing side lengths based on a scale factor. Could we determine what the scale factor is? Yeah, what's our scale factor here? 3. Going from little to big, the scale factor is 3. What if I was going from big to little? What would it be?
3.
What? Not negative 3. Point 3 is closer. Which is what fraction? 0.3 repeating, which is the same as 1/3. Okay? Could we have found the scale factor and then solved? Yeah. Is one better than the other? Not really. In my opinion, it kind of makes... It depends on the numbers. Here, can we kind of easily see the relationship between 4 and 12? What if this was 14? If it was 14, I'd use a proportion. If it was 12, it's easier to recognize. Does that make sense?
Yeah.
Yeah? Okay. Any other questions? Can I erase to do another example?
Sure.
Yes. All right. All right, let's look at example 1B. Example 1B. Here we have some quadrilaterals. Can anybody tell me what specific type of quadrilateral we have here? If there is one.
A quadrilateral. I forgot geometry.
It's okay, we're going to come back to it.
Is that wrong? It's called quadrilateral. What is this? A quadrilateral.
It's called the shape.
I'm at 5, 4, 3, 2, 1. You're done? Ladies and gentlemen, believe it or not, this does not have a special name.
It's called
No.
shape.
It does. It is not a special quadrilateral because all 4 interior angles are different. Okay?
It needs a name. How about it needs a name?
We know that these are not special quadrilaterals because all the interior angles are different. So, we know that side length RU is 28 feet. We know that RS is 49 feet. We know that WZ is 4 feet and XW is D feet. What are we solving for? We're solving for D. Alright, so I'm going to set up my proportion as little over big equals little over big. Alright? What is my little dimension here? I need a little dimension. Is it going to be 49, 28, D, or 4?
It's 4 and D.
Okay, so we could either use 4 or D. We haven't done many problems with the variable on the left side, so let's use D first. Alright, and what is the corresponding side that goes with D in my big shape? 49. D over 49 equals my little 4 and my big
28.
28. What do I need to do? Cross multiply. Thank you. When I cross multiply, what does my first line of work look like? Yes, sir.
49 times 4.
49 times 4
Equals D.
equals what?
D times
D times 28. Can I write that as 28 times D?
Yes.
Alright, 49 times 4 is?
A number. It's a number.
You're right, it is a number and that number is 196. What is 28 times D? 28D. What comes next?
Divide by 28.
Why am I dividing by 28?
Because we're trying to get rid of the 28.
Because we're trying to get the variable by itself and less number attached, which means that 196 divided by 28 is?
7.
7. What units?
It's my feet.
What feet? Equals D. Alright, what questions do you have?
We're allowed to use a calculator.
Yes, you may use a calculator. Any other questions? Alright, thank you very much.